We can also experimentally test the prediction that changing input statistics should change K. Here is a suggested physiological test. So first of all, find a classical V1 monocular cell that responds only to one eye and gets neither excitation nor inhibition from the other eye, the silent eye. Now let's say this cell is excited by the right eye only, so GR is larger than 0, but the left eye input has no effect, GL equal to 0. Now according to this formula, this G plus and G minus contributes to GL according to this formula, so therefore the two contributions must cancel each other out in the left eye. So now if suddenly G plus is relatively increased, then the silent eye should become facilitatory to the other eye. Or if on the other hand G minus is relatively increased, then the silent eye should become antagonistic to the or opposing to the other eye. So therefore the second stage is what you do is give animal some visual adaptation that should increase the relative gains G plus over G minus or decrease it. You can do that by, for instance, dimming or brightening the experimental room respectively. Then the silent eye should become facilitatory or suppressive, depending on whether you dim or brighten the room, and to the dominant eye for this particular neuron's activities. Let's look at some examples of psychophysical tests. This means that we need to look at the behavioral manifestations of the changes in G plus and G minus sensitivities, which adapt to changes in visual input statistics. And the idea is to create visual inputs to two eyes such that the summation channel and the difference channel signals should lead to very different perceptions, perception A or perception B respectively. This is like perceptual rivalry, not between images of the left and right eyes, but between the summation image and the difference image. So this is an ambiguous perception. So if we ask observers what they see, A or B, and if they have to answer by false choice, they might answer A in some trials and answer B in other trials. The chance that they will answer A should increase with the sensitivity G plus relative to the sensitivity G minus. And the sensitivities depend on the signal power, which we know that it depends on the correlation coefficient R between the inputs to the two eyes. So if we consider the zero noise condition, we have whitening so that the gains are inversely related to signal power. Then we have this dependence of the relative gains on the correlation coefficient R. So therefore we have this prediction. Okay, if we change R, let's say we increase it, and then observers will see A less often, but if we decrease it, then they will see this perception A corresponding for the inputs of the summation channel more often. Here's an example of such visual inputs. We put flashing gratings in the two eyes, and they differ from each other in their flashing temporally and spatially this way. Okay, so they differ temporally by 90 degrees in phase and spatially also by 90 degrees in phase. And this design is such that if you add these two gratings together, the summation signal is drifting grating, drifting in one direction. And if you subtract these two gratings from each other, you will get a drifting grating drifting in the other direction. Just look at that, And then you can just ask the observers whether they see the grating drifting up or drifting down. Okay, and then we can then adapt the observers to an environment in which the correlation coefficient R is different. And then their chance of seeing the drifting direction for the summation channel should then change accordingly. To test this prediction, there should be two stages. First is an adaptation stage to let observers see visual images which have a different correlation coefficient R. For example, you can make observers see identical images in the two eyes. Okay, this should make this correlation coefficient R equal to 1. And you can make sure they do see identical images by letting them wearing stereo goggles, and you can control exactly which image each eye sees. Here is another example. The image is shown to the left eye is a photonegative of the image shown to the right eye, and this should cause correlation coefficient R equal to -1. Or you can adapt them to seeing independent images in the two eyes to make R equal to 0. And you don't have to use these photographic images. You can also use random noise images as long as the two eyes see exactly the same image in this condition and see photonegatives of each other in this condition and independent in that condition. Yeah. Now, after the adaptation, if the efficient coding theory is correct, and then the gains G plus G minus should change, and now we move to the testing stage. We just measure observers' chances of seeing the drifting direction one way or another way. Yeah. So from trial to trial, you make this summation and drift in drifting up in some trials and drifting down in other trials randomly. And but it's always drifting in the opposite direction as the difference channel. And then you measure the probability that observers seeing the drifted direction as the same as the summation channel. So if the prediction is correct, then we should see that the chance of seeing the drifting direction consistent with the summation signal is largest in this situation when after you adapt to these opposite images to the two eyes, and smallest this chance when after adapting to identical images to the two eyes, and intermediate after such adaptation. And so such changes in as a result of adaptation is quite unusual, since we let observers see static images during adaptation, but such adaptation causes their visual perception to change on visual motion. Yeah, and that's quite unexpected. So if we do observe such perceptual changes in visual motion, then they should provide quite strong support to the theory. The predictions were experimentally tested. This shows the timeline of experimental stages and trials. During adaptation, the observers viewed dichotic images of particular ocular correlation R. These image pairs were shown one after another as if in a slideshow. Interestingly, a couple of minutes of seeing these images was enough to alter the efficient coding in the brain. After adaptation, this is how a test trial was like. We show the observer a brief test dichotic input grating, and then the observer report whether the perceived grating was going up or down. And this was then repeated over many trials to get the average probability of seeing the summation signal. At the beginning of each of such testing trials, some top-up adaptation was provided to maintain the adaptation state. Indeed, the chance of seeing the summation drift direction was dramatically altered by such an adaptation, just as predicted. The predictions have also been confirmed using other visual input designs. For example, using such input to the two eyes, the summation and difference channels should see gratings tilted one way and another. Or using such inputs to the two eyes, left and right eye, then you should see different facial emotions, happy face or sad face, in the two different channels, summation and difference channels. And these kind of adaptations can also alter the perceived stereo depths. And this is because changing the gains G plus and G minus through adaptation also changes the efficient coding as manifested in the disparity tunings of the V1 neurons. And this disparity tuning is a coding combining spatial coding and ocularity coding. We will explain this in another part of the course.